Chapter 2, Some Basic Chemistry. When you hear or see the word chemistry, you may think of test tubes and breakers or beakers in a laboratory experiment. For our study of the human body, however, let us think of our laboratory as a kitchen with pots and pans and good food simmering on the stove or baking in the oven. The scents of that food are carried in the air, which is a mixture of gaseous chemicals that we inhale and exhale. The pots and pans, as well as the paper of a cookbook, once the wood of a tree, are solid chemicals that we inhale are solid chemicals. Water is a liquid chemical, and all of our foods are chemicals. Recall from chapter 1 that the simplest level of organization is the chemical level. Our bodies are complex arrangements of thousands of chemicals. Where do we obtain new chemicals to make new body parts or supply energy? That's right, from food. Many people consider good cooking an art, and so it may be, but good cooking is also a science, in parentheses, as you will see with rice and eggs later in this chapter, close parentheses. The science of chemistry. And eating, it's all chemistry. This chapter covers some very basic aspects of chemistry as they are related to living organisms and most especially as they are related to our understanding of the human body. So try to think of chemistry not as a complicated science, but rather as the air, water, and food we need in every substance that is part of us. Before we get to food groups, however, we must begin with the fundamentals of chemical structure, the atoms of elements and the bonds that hold them together. Elements. All matter, both living and non-living, is made up of elements, the simplest chemicals. An element is a substance made up of only one type of atom. Therefore, an atom is the smallest part of an element. There are 92 naturally occurring elements in the world around us. Examples are hydrogen, iron, oxygen, calcium, nitrogen, and carbon. In nature, an element does not usually exist by itself, but rather combines with the atoms of other elements to form compounds. Examples of some atoms important to our study of the human body are water, in which two atoms of hydrogen combine with one atom of oxygen; carbon dioxide, in which an atom of carbon combines with two atoms of oxygen; and glucose, in which six carbon atoms and six oxygen atoms combine with 12 hydrogen atoms. The elements carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are found in all living things. If calcium is included, these seven elements make up approximately 99% of the human body, which is the weight. More than 20 different elements are found in varying amounts in the human body. Some of these are listed in Table 2.1. Note, many of these are already familiar to you. Become familiar with all of these abbreviations. As you can see, each element has a standard chemical symbol. This is simply the first and sometimes the second letter of the element's English or Latin name. You should know the symbols of the elements in this table because they are used in textbooks, articles, hospital laboratory reports, and so on. Notice that if a two-letter symbol is used for an element, the second letter is always lowercase, not a capital. For example, the symbol for calcium is Ca, not C capital A. C capital A is an abbreviation often used for cancer. Atoms. Atoms are the smallest part of an element that have the characteristics of that element. An atom consists of three major subunits or particles: protons, neutrons, and electrons. A proton has a positive electrical charge and is found in the nucleus or center of the atom. A neutron is electrically neutral, has no charge, and is also found in the nucleus. An electron has a negative electrical charge and is found outside the nucleus, orbiting in what may be called an electron cloud or energy level or shell around the nucleus. The number of protons in an atom gives it its atomic number. Protons and neutrons have mass and weight. They give atom its atomic weight. In an atom, the number of protons, plus sign, equals the number of electrons, negative sign. Therefore, an atom is electrically neutral. The electrons, however, are important in that they may enable an atom to connect or bond to other atoms to form molecules. A molecule is a combination of atoms, usually of more than one element, that are so tightly bound together that the molecule behaves as a single unit. Each atom is capable of bonding in only very specific ways. This capability depends on the number and the arrangement of the electrons of the atom. Electrons orbit the nucleus of an atom in shells or energy levels. The first or innermost energy level can contain a maximum of 2 electrons and is then considered stable. The second energy level is stable when it contains its maximum of 8 electrons. The remaining energy levels more distant from the nucleus are also most stable when they contain 8 electrons or a multiple of 8. A few elements are naturally stable or uninterested uninterested in reacting because their outermost energy level already contains the maximum number of electrons. The gases helium and neon are examples of these stable, inert atoms, which do not usually react with other atoms. Most atoms are not stable, however, and tend to gain, lose, or share electrons in order to fill their outermost shell. By doing so, an atom is capable of forming one or more chemical bonds with other atoms. In this way, the atom becomes stable because its outermost shell of electrons has been filled. It is these reactive atoms that are of greatest interest in our study of anatomy and physiology. Takeaways. The bonding capabilities of atoms depend upon the number of their fill in the blank. 2. Name the elements represented by these symbols: C, Ca, Cl, Co, Cu, H. Name the elements represented by these symbols: Fe, K, N, Na, O, P, S. Which 6 of the above elements are found in all living things? Chemical bonds. A chemical bond is not a structure, but rather a force or attraction between positive and negative electrical charges. A chemical bond keeps 2 or more atoms closely associated with each other to form a molecule. By the way of comparison, think of gravity. We know that gravity is not a thing we can see or hold, but rather the force that keeps our feet on the floor and allows us to pour coffee with consistent success. Molecules formed by chemical bonding often have physical characteristics different from those of the atoms of the original element. For example, the elements hydrogen and oxygen are gases, but atoms of each may chemically bond to form molecules of water, which is a liquid. The type of chemical bonding depends on the tendencies of the electrons of atoms involved. As you will see, 4 kinds of bonds are very important to the chemistry of the body: ionic bonds, covalent bonds, disulfide bonds, and hydrogen bonds. Ionic bonds. An ionic bond involves the loss of one or more electrons by one atom and the gain of the electron or electrons by another atom or atoms. Refer to figure 2.2 as you read the following. An atom of sodium, Na, has 1 electron in its outermost shell, and in order to become stable, it tends to lose the electron. When it does so, the sodium atom has 1 more proton than it has electrons. Therefore, it now has an electrical charge or valence of +1 and is called a sodium ion, Na+. An atom of chlorine and has 7 electrons in its outermost shell. And in order to become stable, it tends to gain 1 electron. When it does so, the chlorine atom has one more electron than it has protons and now has a charge, valence, of -1. It is called a chloride ion, Cl negative sign. When an atom of sodium loses an electron to an atom of chlorine, their ions have unlike charges, positive and negative, and are thus attracted to one another. The result is the formation of a molecule of sodium chloride, NaCl, or common table salt. The bond that holds these ions together is called an ionic bond. Another example is the bonding of chlorine to calcium. An atom of calcium has 2 electrons in its outermost shell and tends to lose those electrons in order to become stable. If 2 atoms of chlorine each gain one of those electrons, they become chloride ions. The positive and negative ions are then attracted to one another, forming a molecule of calcium chloride, CaCl2, which is also a salt. A salt is a molecule made of ions other than hydrogen ions or hydroxyl ions. Ions with positive charges are called cations. These include Na+, Ca+, K+, Fe+2, and Mg+2. Ions with negative charges are called anions, which include Ci negative, SO4 -2 sulfate, and HCO3 negative bicarbonate. The types of compounds formed by ionic bonding are inorganic salts, acids, and bases. Acids and bases are discussed later in this chapter. If the solid state ionic bonds are relatively strong, our bones, for example, contain the salt calcium carbonate, CaCO3, CaCO3, which helps give bone its strength. In an aqueous solution, aqueous meaning water, however, many ionic bonds are weakened. The bonds may become so weak that the bound ions of a molecule separate, creating a solution of free positive and negative ions. For example, if sodium chloride is put in water, it dissolves and then ionizes. The water now contains Na plus ions and Cl negative ions. Ionization is also called dissociation. It's important to live in organisms because the ions produced are free to take part in other chemical reactions within the body. Cells in the stomach lining must have Cl negative ions to produce hydrochloric acid, HCl. The chloride in NaCl would not be free to take part in another reaction because it is tightly bound to the sodium atom. However, the Cl negative ions available from ionized NaCl in the cellular water can be used for the synthesis of chemical manufacture of HCl in the stomach. Covalent bonds. Covalent bonds involve the sharing of electrons between atoms. As shown in figure 2.3, an atom of oxygen needs 2 electrons to become stable. It may share 2 of its electrons with another atom of oxygen, also sharing 2 electrons. Together they form a molecule of oxygen gas, O2, which is the form in which oxygen exists in the atmosphere. An atom of oxygen may also share 2 of its electrons with 2 atoms of hydrogen, each sharing a single electron. Together they form a molecule of water. When writing structural formulas for chemical molecules, a pair of shared electrons is indicated by a single line. As shown in figure 2.3, the formula for water, this is a single covalent bond. A double covalent bond is indicated by 2 lines, as in the formula for oxygen. This represents 2 pairs of shared electrons. The element carbon always forms covalent bonds. An atom of carbon has 4 electrons to share with other atoms. If these 4 electrons are shared with 4 atoms of hydrogen, each sharing its 1 electron, a molecule of methane gas is formed. Carbon may form covalent bonds with other carbons, hydrogen, oxygen, nitrogen, and other elements. Organic compounds such as proteins and carbohydrates are complex and precise arrangements of these atoms, covalently bonded to one another. Covalent bonds are relatively strong and are not weakened in an aqueous solution. This is important because the proteins produced by the body in muscle and skin, for example, must remain intact in order to function properly in the water of our cells and bloods. The function of organic compounds will be considered later in this chapter. Disulfide bonds and hydrogen bonds. Two other types of bonds that are important to the chemistry of the body are disulfide bonds and hydrogen bonds. Disulfide bonds are found in some proteins. Hydrogen bonds are part of many different molecules. A disulfide bond, also called a disulfide bridge, is a covalent bond formed between two atoms of sulfur, usually within the same large protein molecule. The hormone insulin, for example, is a protein that must have a very specific three-dimensional shape in order to function properly to regulate the blood glucose level. Each molecule of insulin has two disulfide bonds that help maintain its proper shape and function. Other proteins with shapes that depend upon disulfide bonds are the antibodies produced by cells of the immune system and keratin produced by cells of the skin and hair. A strand of hair maintains its shape because of these sulfide bonds. When naturally curly hair is straightened, the disulfide bonds in the keratin molecules are broken. When naturally straight hair is permed or curled, the disulfide bonds in the keratin are first broken, then reformed in the curl hair. Neither process affects the living part of the hair root, so the hair will grow out in its original shape. We would not want to we would not want such a process affecting our insulin or antibody molecules, for that would destroy their functioning. A hydrogen bond does not involve the sharing or exchange of electrons, but rather results from a property of hydrogen atoms. When a hydrogen atom shares its one electron in a covalent bond with another atom, its protein has slight positive charge and may then be attracted to a nearby oxygen or nitrogen atom, which has a slightly negative charge. Although they are weak bonds, hydrogen bonds are important in several ways. Large organic molecules such as proteins and the DNA in our chromosomes have very specific functions that depend upon their three-dimensional shapes. These shapes, the shapes of these molecules, so crucial to their proper functioning, are often maintained by hydrogen bonds. Hydrogen bonds also make water cohesive. Cohesion is the tendency of similar molecules to stick to one another in a glass of water. For example, each water molecule is attracted to nearby water molecules. One water molecule forms up to four hydrogen bonds, one with each of four other water molecules. Each of those four molecules can form four hydrogen bonds and so on, making all of the water cohesive. Water can also be adhesive with other molecules. Adhesion is the tendency of unlike molecules to be attracted to one another. If you have ever built a sandcastle at the beach, you know that it is quite sturdy when the sand is wet, but becomes fragile as the sand dries. Both the cohesion and adhesion capability of water molecules help keep the grains of wet sandcastle together. The cohesiveness of water itself can be seen if water dropped into clean glass. The surface tension created by the hydrogen bonds makes the water form three-dimensional beads. Within the body, the cohesiveness of water helps keep blood a continuous stream as it flows within the blood vessels and also keeps tissue fluid continuous around cells. These hydrogen bonds are also responsible for the other important characteristics of water, which are discussed in a later section. Chemical reaction. A chemical reaction is a change brought about by the formation of breaking of chemical bonds. Two general types of reaction are synthesis reaction and decomposition reactions. In a synthesis reaction, bonds are formed to join two or more atoms of molecules to make a new compound. The production of the protein hemoglobin in potential red blood cells is an example of a synthesis reaction. Proteins are synthesized by the bonding of many amino acids. Their smaller subunits. Synthesis reaction require energy for the formation of bonds. In a decomposition reaction, bonds are broken and a large molecule is changed to two or more smaller ones. One example is the digestion of large molecules of starch into many smaller glucose molecules. Some decomposition reactions release energy. This is described in a later section of cell respiration. Within cells, synthesis is often coupled with decomposition. When membranes or other cell parts break down, they must be replaced. The old or damaged structures may be recycled for their smaller parts or subunits. These parts can be minerals, such as iron, or organic molecules, such as amino acids, and can be used in subsequent synthesis reactions. When older hemoglobin breaks down, for example, its iron can be used over and over to synthesize new hemoglobin for red blood cells. In this and future chapters, keep in mind that the term reaction refers to the making or breaking of chemical bonds, and thus to change in the physical and chemical characteristics of the molecules involved. Takeaways. 1. What type of chemical bond involves sharing of electrons? What type involves the attraction of unlike charges? 2. In what type of chemical reaction are new bonds formed? 3. Which type of chemical reaction is more likely to require energy? 4. The cohesiveness of water depends on what type of chemical bonds. Inorganic compounds of importance. Inorganic compounds are usually simple molecules that often consist of only one or two different elements. Despite their simplicity, however, some inorganic compounds are essential to normal structure and functioning of the body. Water. Water makes up 55% to 70% of the human body and is essential to life for several reasons. 1. Water is a solvent. That is, many substances called solutes can dissolve in water. Nutrients such as glucose are dissolved in blood plasma, which is largely water, to be transported to cells throughout the body. The excretion of waste products is possible because the products are dissolved in the water of urine produced by the kidneys. The senses that enable us to enjoy our food, taste, and smell both depend upon the solvent ability of water. Food molecules dissolved in saliva stimulate receptors and taste buds on the tongue. Vaporized food molecules, especially from hot foods, are sniffed into the upper nasal cavities, where they dissolve in the thin film of water and stimulate olfactory receptors. Hot foods often seem more tasty than cold foods because the sense of smell contributes more to our perception of them. 2. Water is a lubricant, which prevents friction where surfaces meet and move. The hydrogen bonds of adjacent water molecules, in parentheses, their cohesiveness, close parentheses, contribute significantly to this function. In the digestive tract, for example, swallowing depends on the presence of saliva. The mucus is a slippery fluid that permits the smooth passage of food through the intestines. Synovial fluid within joint cavities prevent friction as bones move. 3. Water changes temperature slowly. Water has a high heat capacity, which means that it will absorb a great deal of heat before its temperature rises significantly, or it must lose a great deal of heat before its temperature drops significantly. This is one of the factors that help the body maintain a constant temperature. Water also has a high heat of vaporization, the heat needed to change water from a liquid to a gas. This is important for the process of sweating. Excess body heat evaporates sweat on skin surfaces. rather than overheating the body's cell. And because of water's high heat of vaporization, a great deal of heat can be given off with the loss of relatively small amount of water. Water compartments. All water within the body is continually moving, but water is given different names when it is in specific body locations, which are called compartments. Intracellular fluid, ICF, the water within cells, about 65% of the total body water. Extracellular fluid, ECF, all the rest of the water in the body, about 35% of the total. More specific compartments of extracellular fluid include the following: plasma, water found in blood vessels; lymph, water found in lymphatic vessels; tissue fluid or interstitial fluid, water found in the small spaces between cells. Specialized fluids: synovial fluids in joints, cerebrospinal fluid around the brain and spinal cord, aqueous humor in the eye, and others. The movement of water between compartments in the body and the function of the specialized fluids will be discussed in later chapters. Oxygen. Oxygen in the form of gas is approximately 21% of the atmosphere, which we inhale. We all know that without oxygen, we wouldn't survive very long, but exactly what does oxygen do? Oxygen is important to us because it is essential for a process called cell respiration, in which cells break down simple nutrients such as glucose in order to release energy. The reason we breathe is so to obtain oxygen for cell respiration and to exhale the carbon dioxide produced in cell respiration. This will be discussed in the next section. Biologically useful energy that is released by the reactions of cell respiration is trapped in a molecule called ATP, adenosine triphosphate. ATP can then be used for cellular processes that require energy. Carbon dioxide. Carbon dioxide, CO2, is produced by cells as a waste product of cell respiration. You may ask why a waste product is considered important. Keep in mind that important does not always mean beneficial. Instead, it can mean significant. And the amount of carbon dioxide in the body fluids increases, it causes these fluids to become too acidic. Therefore, carbon dioxide must be exhaled as rapidly as it is formed to keep the amount in the body within normal limits. Normally, this is just what happens, but severe pulmonary diseases such as pneumonia or emphysema decrease gas exchange in the lungs, resulting in the accumulation of carbon dioxide in the blood. When this happens, a person is said to be in a state of acidosis, which may seriously disrupt body functioning. Cell respiration. Cell respiration is the name of energy production within cells and involves both respiratory gases, oxygen and carbon dioxide. Many chemical reactions are involved, some of which take place in cell organelles or mitochondria. In its simplest form, cell respiration may be summarized by the following equation: glucose, C6H12O6, plus 6O2 forms 6CO2 plus 6H2O plus ATP plus heat. This reaction shows us that glucose and oxygen combine to yield carbon dioxide, water, ATP, and heat. Food, represented here by glucose, in the presence of oxygen is broken down into simpler molecules, carbon dioxide and water. The potential energy in the glucose molecule is released in two forms: ATP and heat. Each of the four products of this process has a purpose or significance in the body. The carbon dioxide is a waste product that moves from the cells into the blood, which carries it to the lungs where it is eventually exhaled. The water formed is useful and becomes part of an intracellular fluid. The heat contributes to normal body temperature. ATP is used for cell processes such as mitosis, protein synthesis, and muscle contraction, all of which require energy and will be discussed a bit further on in the text. We will also return to cell respiration in later chapters and to mitochondria in chapter 3. For now, the brief description just given will suffice to show that eating and breathing are interrelated. Both are essential for energy production. Trace elements. Trace elements are those that are needed by the body in very small amounts. When they are present in food or nutritional supplements, we often call them minerals. Examples are iron, found in meat and legumes; cobalt, found only in animal foods such as liver and fish; magnesium, found in green vegetables because it is a part of chlorophyll; and iodine, found in seafood and iodized salt. Although trace elements may not be as abundant in the body as carbon, hydrogen, and oxygen, they are nonetheless essential. Table 2.2 lists some of these trace elements and their functions. Calcium and phosphorus, found in milk, ice cream, cheese, meat, and fish, are included in this table, though they are needed in somewhat larger amounts than are the others. Note, table 2.2 is a table to be learned, not this minute perhaps, but soon, and some of it you already know. The information is important, but is presented as a table rather than in paragraph form because a list format is often simpler to grasp visually and therefore mentally. You will come across every one of these elements and their function in later chapters, and when you do, you may be able to say to yourself, aha, I already knew that. Acids, bases, and pH. An acid may be defined as a substance that increases the concentration of hydrogen ions, H+, in a water solution. A base is a substance that decreases the concentration of H+ ions, which in the case of water has the same effect as increasing the concentration of hydroxyl ions, OH negative. The acidity of or alkalinity, basicity or basicity. The acidity or alkalinity, basicity of a solution is measured on a scale of values called pH, parts hydrogen. The values on the pH scale range from 0 to 14, with 0 indicating the most acidic level and 14 the most alkaline. A solution with a pH of 7 is neutral because it contains the same number of H+ ions and OH negative ions. Pure water has a pH of 7. A solution with a higher concentration of H+ ions than OH negative ions is an acidic solution with a pH below 7. An alkaline solution, therefore, has a higher concentration of OH negative ions than H+ ions and has a pH above 7. The pH scale with the relative concentration of H+ ions and OH ions is shown in figure 2.5. A change of 1 pH unit is a tenfold change in H+ ion concentration. This means that a solution with a pH of 4 has 10 times as many H+ ions, a solution of pH of 5, and 100 times as many H+ ions as a solution with a pH of 6. Figures 2.5 also show the pH of some body fluids and other familiar solutions. Notice that gastric juice has a pH of 1 and coffee has a pH of 5. This means that gastric juices has 10,000 times as many H+ ions as coffee has. Although coffee is acidic, it is a weak acid and does not have the corrosive effect of gastric juice, a strong acid. The cells and internal fluids of the human body have a pH close to a neutral. The pH of intracellular fluid is around 6.8 to 7.0, and the normal pH range of blood is 7.35 to 7.45. Fluids such as gastric juice and urine are technically external fluids because they are in body tracts that open to the environment. The pH of these fluids may be more strongly acidic or alkaline without harm to the body. The pH of blood, however, must be maintained within its very narrow, slightly alkaline range. A decrease of only 1 pH unit, which is 10 times as many H plus ions, would disrupt the chemical reactions of the blood and cause the death of the individual. Normal metabolism tends to make body fluids more acidic, and to this tendency to acidosis must be continually corrected. Normal pH of internal fluids is maintained by the kidneys, respiratory system, and buffer systems. Although acid-base balance will be a major topic of Chapter 19, we will briefly mention buffer systems here. Buffer systems. A buffer system is a chemical or pair of chemicals that minimizes changes in pH by reacting with strong acids or strong bases to transform them into substances that will not drastically change pH. Expressed in another way, a buffer may bond to H plus ions when a body fluid is becoming too acidic, or release H plus ions when a fluid is becoming too alkaline. We will use the bicarbonate buffer system as a specific example. This system consists of carbonic acid, H2CO3, a weak acid, and sodium bicarbonate, NaHCO3, a weak base. This pair of chemicals is present in all body fluids, but is especially important to buffer blood and tissue fluid. Carbonic acid ionizes as follows, in parentheses, but remember, because it is a weak acid, it does not contribute many H plus ions to a solution, close parentheses. H2CO3 goes to H plus HCO3, negative. Sodium bicarbonate ionizes as follows. NaHCO3 goes to Na plus HCO3 negative. If a strong acid such as HCl is added to extracellular fluid, the following reaction will occur. HCl plus NaHCO3 goes to NaCl plus H2CO3. What has happened here? The hydrochloric acid, a strong acid that will greatly lower pH, has reacted with sodium bicarbonate. The product of this reaction are NaCl, a salt that has no effect on pH, and H2CO3, a weak acid that lowers pH only slightly. This prevents a drastic change in the pH of the extracellular fluid. If a strong base, such as sodium hydroxide, is added to the extracellular fluid, this reaction will occur. NaOH plus H2CO3 goes to H2O plus NaHCO3. Sodium hydroxide, a strong base that will greatly rise pH, has reacted with carbonic acid. The products of this reaction are water, which has no effect on pH, and sodium bicarbonate, a weak base that raises pH only slightly. Again, this prevents a drastic change in the pH of the extracellular fluid. In the body, such reactions take place in less than a second whenever acids or bases are formed that will greatly change pH. Because of the body's tendency to become more acidic, the need to correct acidosis is more frequent. With respect to the bicarbonate buffer system, this means that more NaHCO3 than H2CO3 is needed. For this reason, the usual ratio of these buffers is 20:1. NaHCO3 to H2CO3. Takeaways. 1. Oxygen is essential for humans for the process of fill in the blank. A pH of 7.4 is slightly fill in the blank. 3. Which trace element or mineral is part of the hormone thyroxine, which is part of vitamin B12? Which one is needed for blood clotting? 4. The process of cell respiration as a whole can be considered a fill in the blank reaction because it releases fill in the blank. Organic compounds of importance. For many newborns throughout the world, their first meal is their mother's breast milk, and their next meal and the next. If a mother is healthy and well nourished, her infant can grow and thrive for months or even a few years on breast milk alone. Why is human breast milk such a complete food for humans only? Let's look at what it consists of in addition to the inorganics, the minerals such as calcium and sodium, and lots of water. Milk contains the sugar lactose, and more complex carbohydrates, fats, and several kinds of various types of proteins and vitamins. These are sufficient to meet all of an infant's nutritional needs, and all of these are organic compounds. Organic compounds all contain covalently bonded carbon and hydrogen atoms and perhaps other elements as well. In the human body, there are many types of organic compounds, but the four major groups are carbohydrates, lipids, proteins, and nucleic acid. Carbohydrates. A primary function of carbohydrates is to serve as sources of energy and cell respiration. All carbohydrates contain carbon, hydrogen, and oxygen are classified as monosaccharides, disaccharides, or oligosaccharides, and polysaccharides. Saccharide means sugar, and the prefix indicates how many are present. Monosaccharides are single sugar compounds, are the simplest sugars. Glucose is a hexose or 6-carbon sugar with the formula C6H12O6. Fructose and galactose also have the same formula, but the physical arrangement of the carbon, hydrogen, and oxygen atoms in each differs from that of glucose. This gives each hexose sugar a different three-dimensional shape. The honey produced by bees contains fructose and glucose. Sweet fruits contain fructose. Glucose does not taste very sweet to us. Galactose is usually part of the disaccharide lactose in milk. The liver is able to change fructose and galactose to glucose, which is then used by cells in the process of cell respiration to produce ATP. Another type of monosaccharide is the pentose, or 5-carbon sugar. These are not involved in energy production, but rather are structural components of the nucleic acids. Deoxyribose is part of DNA, which is a genetic material of chromosomes. Ribose, C5H10O5, is part of RNA, which is essential for protein synthesis. We will return to the nucleic acids later in this chapter. Disaccharides are double sugars made of two monosaccharides linked by a covalent bond. When that bond is formed, a molecule of water, HOH, is removed. So the general formula of a disaccharide is not quite twice that of a glucose molecule. It is C12H22O11. Sucrose, or cane sugar, for example, is made up of one glucose and one fructose. It is also found in beets and other vegetables. Lactose is made up of one glucose and one galactose. It is found in milk, ice cream, whipped cream, and other milk products. The grain sugar maltose is made up of two glucose molecules. Disaccharides in our food are digested into monosaccharides that are then used for energy production. The prefix oligo means few. Oligosaccharides consist of 3 to 20 monosaccharides and perhaps additional carbon-hydrogen chains attached. Unlike other carbohydrates, oligosaccharides are not sources of energy for us because we cannot digest them. In human cells, oligosaccharides are found on the outer surface of cell membranes. Here they serve as antigens, which are chemical markers or signposts that identify cells. The A, B, and AB blood types, for example, are the result of oligosaccharide antigens on the outer surface of red blood cell membranes. As you may know, type O RBCs have neither A nor B antigens. All of our cells have self-antigens that identify the cells that belong in an individual. The presence of self-antigens on our own cells provide a comparison for the white blood cells of the immune system to use with foreign material. The white blood cells are then able to recognize antigens that are non-self. Such foreign antigens include bacteria and viruses, and immunity will be a major topic of chapter 14. Different oligosaccharides are produced by the cells of the mammary glands and become part of breast milk. These carbohydrates are not meant to nourish the breastfed infant. Milk contains lactose for the baby, but rather to encourage the growth of beneficial bacteria in the infant's intestines. The newborn's intestines are sterile, but bacteria arrive with every swallow, and the good bacteria digest oligosaccharides and convert parts to fatty acids that may contribute to the growth of an infant's nervous system. Recall from chapter 1 that such bacteria, our microbiota or normal flora, are thought to have a part in maintaining the health of the intestinal tract lining throughout life, as well as to strengthening and sustaining aspects of immunity. Polysaccharides are made of thousands of glucose molecules bonded in different ways, resulting in different shapes. Starches are branded chains of glucose and are produced by plant cells to store energy. Potatoes, rice, corn, and wheat all contain useful starches. Nearly every human culture has learned to cultivate a major crop to be a source of starch. Rice is often eaten simply after being boiled, and it must be cooked. Humans cannot digest raw rice, but cooking is chemistry, and boiling softens the cellulose cell walls and bursts the cells in the rice grains, releasing their starch in a form that is digestible. We consume other starches as part of bread, pasta, pizza crust, noodles, French fries, baked potatoes, and dumplings, as well as cookies, cakes, and pies. Humans have the digestive enzymes that split the bonds of starch molecules, releasing glucose. The glucose is then absorbed and used by cells to produce ATP. Glycogen, a highly branched chain of glucose molecules, is our own storage form for excess glucose. After a meal high in carbohydrates, the blood glucose level rises. If the level were to remain high, glucose would be lost as the kidneys excreted it in the urine. In parentheses, this is what happens in diabetes, close parentheses. But with the presence of the hormone insulin, excess glucose in the blood is quickly removed from the blood, changed to glycogen, and stored in the cells of the liver and skeletal muscles. When the blood glucose level decreases between meals, the glycogen is converted back to glucose, which is released into the blood. In parentheses, these reactions are regulated by other hormones, close parentheses. The blood glucose level is kept within normal limits, and cells can take in this glucose to produce energy. Cellulose is a nearly straight chain of glucose molecules produced by plant cells as part of their cell walls. We have no enzyme to digest the cellulose we consume as part of fruits and vegetables, such as apples, pears, beans, broccoli, and peas, grains, and nuts. So it passes through the digestive tract unchanged. Many raw vegetables and nuts, such as carrots or walnuts, are crunchy. What we are crunching is cellulose. Even fruits that are not especially crunchy, such as peaches or strawberries, contain quite a bit of cellulose. Another name for dietary cellulose, in parentheses, and other plant cell wall components such as pectin, close parentheses, is fiber. And although we cannot use its glucose for energy, it does have a function. Fiber provides bulk within the cavity of the large intestines. This promotes efficient peristalsis, the waves of contraction that propel undigested material through the colon. A diet low in fiber does not give the colon much exercise, and the muscle tissue of the colon will contract weakly, just as our skeletal muscles will become flabby without exercise. A diet high in fiber provides exercise for the colon muscle and may help prevent chronic constipation. Plant fiber also provides food for our intestinal bacteria. They do have enzymes to break down these complex carbohydrates. These The structure and functions of the carbohydrates are summarized in Table 2.3. Note, this is indeed a summary table. All the information it contains has just been presented in narrative form. This list type is a little different, yet is very similar to sections on carbohydrates in the study outline at the end of the chapter. You may prefer a more abbreviated form when studying. Deciding on the best way for you to learn, and it may not be the same for every topic, is something for you to keep in mind as you read, attend class, and study. Lipids. Lipids contain the elements carbon, hydrogen, and oxygen. Some also contain phosphorus. The group of organic compounds include different types of substances with very different functions. We will consider three types: true fats, phospholipids, and steroids. True fats, also called neutral fats, are made of one molecule of glycerol and one, two, or three fatty acid molecules. Glycerol is a small 3-carbon molecule, C3H8O3. A fatty acid is a long molecule that has an even number of carbons from 12 to 24 bonded to hydrogens, with the first carbon a carboxyl group, COOH. If 3 fatty acid molecules are bonded to a single glycerol, a triglyceride is formed. 2 fatty acids and a glycerol form a diglyceride, and 1 fatty acid and a glycerol form a monoglyceride. The fatty acids in a true fat may be saturated or unsaturated. Refer to figure 2.7 and notice that one of the fatty acids has single covalent bonds between all of its carbon atoms. Each of these carbons is then bonded to the maximum number of hydrogens. This is a saturated fatty acid, meaning saturated with hydrogen. The other fatty acids shown have one or more double covalent bonds between their carbons and less than the maximum number of hydrogens. These are unsaturated fatty acids. Many triglycerides contain both saturated and unsaturated fatty acids, and although not as precise, it is often easier to speak of saturated and unsaturated fats, indicating the predominance of one or the other type of fatty acid. At room temperature, saturated fats are often in solid form, whereas unsaturated fats are often, but not always, in liquid form. Saturated fats tend to be found in animal-based foods such as beef, pork, chicken, eggs, cheese, and ice cream, but palm oil and coconut oil are also saturated. Unsaturated fats are found in other plant oils such as corn oil, sunflower oil, and safflower oil, but certain fish oils are also unsaturated, and even pork contains some unsaturated acids. Unsaturated fats may be changed to saturated fats in order to give packaged foods a more pleasing texture or taste, or to allow them to be stored longer without refrigeration, a longer shelf life. These are hydrogenated fats, meaning that hydrogens have been added, also called trans fat. Trans fat contributes significantly to atherosclerosis of arteries, that is, abnormal cholesterol deposits in the lining that may clog arteries, especially the coronary arteries of the heart. Many food manufacturers have eliminated or are phasing out the use of trans fat in prepared foods. The fat content of foods contributes to the pleasure of eating. The presence of fat gives food a smooth texture. Ice cream, anyone? One reason that many people love ice cream is its smoothness, and low fat forms may have perceptively different texture. May have a perceptively different texture. Of course, ice cream is sweet as well, and impulses from receptors in the mouth for the combination of sweet and smooth activate what are called reward centers in the brain. Eating ice cream is enjoyable, and with the many connections among brain neurons, this information is relayed to many areas. The ice cream experience will be remembered, and the brain will have learned how to obtain more. Within the body, the triglyceride forms of true fats are a storage form for excess food. That is, they are stored energy, potential energy. Any type of food consumed in excess of the body's caloric needs will be converted to fat and stored in adipose tissue. Most adipose tissue is subcutaneous between the skin and muscles. Some organs, however, such as the eyes and kidneys, are enclosed in a layer of fat that acts as a cushion to absorb shock. Phospholipids are diglycerides with a phosphate group, PO4, in the third bonding site of glycerol. Although similar in structure to the true fats, phospholipids are not stored energy, but rather structural components of cells. Lecithin is a phospholipid that is part of our cell membranes. Each phospholipid molecule looks like a spear with two tails. The spear is the glycerol, and the phosphate, the tails, are the two fatty acids. Another phospholipid is myelin, which forms the myelin sheath around nerve cells and provides electrical insulation for nerve impulse transmission. The structure of steroids is very different from that of the other lipids. Cholesterol is an important steroid. It is made of four rings in carbon and hydrogen, in parentheses, not fatty acids and glycerol, close parentheses, and is shown in figure 2.7. The liver synthesizes cholesterol. The liver synthesizes cholesterol in addition to the cholesterol we eat in food. Only animal foods such as beef, pork, milk products, and egg yolks contain cholesterol. Vegetarians do not have cholesterol in their diet and depend upon synthesis by the liver. Cholesterol is another significant component of cell membranes and is the procurer raw material for the synthesis of other steroids. In the ovaries or testes, cholesterol is used to synthesize the steroid hormones, estrogen or testosterone, respectively. A form of cholesterol in the skin is changed to vitamin D on exposure to sunlight. Liver cells use cholesterol for the synthesis of bile salts, which emulsify fats in digestion. Despite its link to coronary artery disease and heart attacks, cholesterol is an essential substance for human beings. The structure and function of lipids are summarized in Table 2.4. Proteins are made of smaller subunits or building blocks called amino acids, which all contain the elements carbon, hydrogen, oxygen, and nitrogen. Some amino acids contain sulfur, which permits the formation of disulfide bonds in proteins such as insulin and antibodies. There are about 20 amino acids that make up human proteins. We obtain these amino acids from animal proteins such as beef, chicken, pork, and fish, and from plant proteins such as those found in beans, peas, nuts, corn, and other grains. The structure of amino acid is shown in figure 2.8, and you will notice that they will have several parts in common. Each amino acid has a central carbon atom covalently bonded to an atom of hydrogen, an amino group, NH2, and a carboxyl group, COOH. At the fourth bond of the central carbon is the variable portion of the amino acid, represented by R. The R group may be a single hydrogen atom or a CH3 group or a more complex configuration of carbon and hydrogen and perhaps sulfur. This gives the 20 amino acids a slightly different physical shape. A bond between two amino acids is called a peptide bond, and a short chain of amino acids linked by peptide bonds is polypeptide. A protein may consist of from 50 to thousands of amino acids. The sequence of the amino acids is specific and unique for each protein and is called its primary structure. This unique sequence and the hydrogen bonds and disulfide bonds formed within the amino acid chain determines how the protein will be folded to complete its synthesis. The folding may be simple, a helix, coil, or pleated sheet called the secondary structure, or more complex folding may occur to form a globular protein called the tertiary structure. Myoglobin found in muscles is a globular protein. When complete, each protein has a characteristic three-dimensional shape, which in turn determines its function. Some protein consist of more than one amino acid chain, quaternary structure. Hemoglobin, for example, has 4 amino acid chains. Notice that myoglobin contains an atom of iron. A hemoglobin molecule has 4 iron atoms. Some proteins require a trace element such as iron or zinc to complete their structure and permit them to function properly. Our body proteins have many functions. Some of these are listed in Table 2.5. Note, this is a table with new information and is another table to be learned. A quick reading now will give you an idea of how our organ system depends on proteins. You will come across all of these type of proteins in later chapters. Although we usually do not think of protein as an energy food, if our diet includes more amino acids than necessary for our protein synthesis, those excess amino acids will be converted to simple carbohydrates for immediate energy or even to fat to be stored as potential energy. One very important function of proteins will be discussed further here, the role of protein as enzymes. Enzymes are catalysts. This means that they speed up chemical reactions without the need for an external source of energy such as heat. The many reactions that take place within the body are catalyzed by specific enzymes. All of these reactions must take place at body temperature. The way in which enzymes functions as catalysts is called the active site theory. Keep in mind that a theory is not a guess. A scientific theory is the best explanation for all the available evidence. All the evidence of enzyme functioning supports the active site theory, which states that the shape of an enzyme determines its function. The specific function also includes the shape of the reacting molecules, called substrates. A simple synthesis reaction is depicted in figure 2.9a. Notice that the enzyme has a specific shape, as do the substrate molecules. The active site of the enzyme is the part that matches the shapes of the substrates. The substrate must fit into the active site of the enzyme, and temporary bonds may form between the enzyme and the substrate. This is called the enzyme substrate complex. In this case, two substrate molecules are thus brought close together so that chemical bonds are formed between them, creating a new compound. The product of the reaction, the new compound, is then released, leaving the enzyme itself unchanged and able to catalyze another reaction of the same type. The reaction shown in figure 2.9b is a decomposition reaction. As the substrate molecule bonds to the active site of the enzyme, strain is put on its internal bonds, which break, forming two product molecules and again leaving the enzyme unchanged. Each enzyme unchanged. Each enzyme is specific in that it will catalyze only one type of reaction. An enzyme that digests the protein in food, for example, has the proper shape for that reaction, but cannot digest starches. For starch digestion, another enzyme with a differently shaped active site is needed. Thousands of chemical reactions take place within the body, and therefore we have thousands of enzymes, each with its own shape and active site. The ability of enzymes to function may be limited or destroyed by changes in the intracellular or extracellular fluids in which they are found. Changes in pH and temperature are especially crucial. Recall that the pH of intracellular fluid is approximately 6.8 to 7.0, and that a decrease in pH means that more H plus ions are present. If pH decreases significantly, the excess H plus ions will react with the active sites of cellular enzymes, change their shapes, and prevent them from catalyzing reactions. This is why a state of acidosis may cause the death of cells. The cell's enzymes are unable to function properly. With respect to temperature, most human enzymes have their optimum functioning in the normal range of body temperature, 97 to 99 degrees. A temperature of 106 Fahrenheit, a high fever may break the chemical bonds that maintain the shape of enzymes. If an enzyme loses its shape, it is said to be denatured, and a denatured enzyme is unable to function as a catalyst. Some human enzymes, when denatured by a high fever, may revert to their original shapes if the fever is lowered quickly. Others, however, will not. A high fever may cause brain damage or death because enzymes in the brain have become permanently denatured. A familiar example of irreversible denaturation is a hard-boiled egg. The proteins in the egg white and yolk will never revert to the shapes they were in the raw egg. This kind of cooking as chemistry is also beneficial for us because denatured egg proteins are in shapes that are more digestible and that they will fit our protein digesting enzymes far better than do raw egg proteins. You already know that metals such as lead and mercury are harmful to humans and that both may cause serious damage to the nervous system and other body tissues. These heavy metals are harmful to us because they are very reactive and block the actions of our enzymes. Figure 2.9d depicts what happens. Notice that the heavy metal ion bonds with part of the active site of the enzyme and changes its shape. The substrate molecule cannot fit and the enzyme is useless. Many other chemicals are poisonous to us for the very same reason. They destroy the functioning of our enzymes and essential reactions cannot take place. Nucleic acids, DNA and RNA. The nucleic acids DNA and RNA are large molecules made of smaller subunits called nucleotides. A nucleotide consists of a pentose sugar, a phosphate group, and one of several nitrogenous bases. In DNA nucleotides, the sugar is deoxyribose, and the bases are adenine, guanine, cytosine, or thymine. In RNA nucleotides, the sugar is ribose, and the bases are adenine, guanine, cytosine, or uracil. DNA and RNA molecules are shown in Figure 2.10. Notice that DNA looks somewhat like a twisted ladder. The ladder is two strands of nucleotides called a double helix, two coils. Alternating phosphate and sugar molecules form the uprights of the ladder, and the pair of nitrogenous bases form the rungs. The size of the bases and the number of hydrogen bonds each can form the complementary base pairing of the nucleic acids. In DNA, adenine is always paired with thymine with two hydrogen bonds, and guanine is always paired with cytosine with three hydrogen bonds. DNA makes up the chromosomes of cells and is therefore the genetic code for hereditary characteristics. The sequence of bases in the DNA strand is actually a code of the many kinds of proteins living proteins living things produce. The code is the same in plants and other animals and microbes. The sequence of bases for one protein is called a gene. Human genes are the codes for the proteins produced by human cells. Through many of these genes are also found in other forms of life. We are very much related. The functioning of DNA will be covered in more detail in the next chapter. RNA is often a single strand of nucleotides with uracil nucleotides in place of thymine nucleotides. RNA is synthesized from DNA in the nucleus of a cell, and there are several forms. All carry out their functions in the cytoplasm. RNA copies the genetic code from DNA and helps assemble amino acids into proteins. Protein synthesis will also be discussed in the following chapter. DNA is a very active molecule. All cells synthesize their own proteins in cells that are capable of mitosis, that is, dividing to form two cells. DNA is even more active, making a copy of itself so that each new cell has a full set of chromosomes. You may suspect that with all this activity, some structural mistakes may be made. They are, but DNA molecules are surrounded by enzyme systems that can often repair these mistakes as soon as they occur. RNA molecules are also active, but many are used once, meaning during one process and then are degraded by enzymes. Their nucleotides, however, are often recycled into the specific RNA molecules the cell requires next. ATP, adenosine triphosphate, is a specialized nucleotide that consists of the base adenine, the sugar ribose, and three phosphate groups. Mention has already been made of ATP as a product of cell respiration that contains biologically useful energy. ATP is one of several energy transfer molecules within cells, transferring the potential energy in food molecules to cell processes. When a molecule of glucose is broken down into carbon dioxide and water with the release of energy, the cell uses some of this energy to synthesize ATP. Present in cells are molecules of ADP, adenosine diphosphate, and free phosphate groups. The energy released from glucose is used to loosely bond a third phosphate to ADP, forming ATP, moving right to left in figure 211. While the bond of this third phosphate is again broken and energy is released, moving left to right to figure 211, ATP then becomes the energy source for cell processes such as mitosis, muscle contraction, or protein synthesis for growth and repair. All cells have enzymes that can remove the third phosphate group from ATP to release its energy, forming ADP and phosphate. As cell respiration continues, ATP is resynthesized from ADP and phosphate. ATP formation to trap energy from food and ATP breakdown to release energy for cell processes is a continuing cycle in cells. The structure and functions of the nucleic acids are summarized in Table 2.6. In addition to the four major groups of organic molecules, other types are involved in human metabolism. The most familiar group is probably that of vitamins, chemicals needed in small amounts. Other groups of chemicals are beyond the scope of this book, but a very brief look is provided in box 2.6, coffee, a chemical cornucopia. Takeaways. What is the eventual function of many of the carbohydrates we eat? What other organic molecule contributes to energy storage and where? What aspect of chemicals is most crucial for the normal functioning of enzymes? And 4, within a cell, what structures is DNA located? Within a cell, in what structures is DNA located? Summary. Chemicals may be inorganic, such as water, oxygen and iron, or organic, such as carbohydrates, lipids, proteins, and nucleic acids. All of the chemicals we have just described are considered to be non-living, even though they are essential parts of all living organisms. The cells of our bodies are precise arrangements of these non-living chemicals and yet are considered living matter. The cellular level, therefore, is the next level of organization we will examine.